Hello again, Max, Harry. I will wait to see if we get the full 13 or 14 back that we had. It's looking good. 5 already. 6. I think we're back online. I think we're good in answer to your question, Harry. Yeah, I'm going to just wait a little bit longer because, oh no, it's 4. There were 13 or 14 of us sort of who were clearly here for the whole lesson. And I'll make a decision once we got everyone back in. We'll make a decision about what we do. And yeah, Matthew, I saw that my first stream got 175 views. I'm not quite sure how that happened, but it's surprised me. I expected it to be about 14, the number of people who said they might sign up for this. In answer to your question, Max, that's a good use of our time is to discuss things like that. For A-level physics, you don't need a calculator anything more than the one you would have used at school. You don't need a graphics calculator, and even for doing A-level maths, you don't need a graphics calculator. Just one of those will do. I'm glad to think, Matthew, that you think my 175 views will allow me to access the big dosh. We are up to 8. I'm going to just wait a little bit longer to see who does manage to make it back. And then we might make a decision as to whether we postpone this lesson until tomorrow and just carry on from where we'd left off, which wasn't very far into the lesson, or whether we think it's worth doing a bit of both. We will see. I have no idea what you just wrote, Matthew. And yeah, I saw this theory. I think it was you that first ventured it, Harry, about rags in the Ethernet cable. Anything possible. All I can say is that I magically managed to fix the connection problems at my end by unplugging the router and plugging it back in. So I think that qualifies me as an electrical engineer now. But yes, I managed to solve it by doing that. And it seems to be a fairly stable connection now. We're up to 9. Hello, you 9, whoever you are. I'm going to wait until wait to see if that increases at all. So wait to see if we get back to the 13 that I think we had. What you can do in the meantime is you can tell me how you did on the quiz. You are absolutely fine to lie, by the way, I'll never know. But tell me how you did in the quiz. I'm assuming that the quiz happened before the connection dropped. I think it did. Oh, well done, Max. That's a very good score. And tell me if you wish the one that you got wrong as well, if you remember what the question was. Up to 10, it's looking good. Hello again. I'm just going to wait a couple of minutes because I think we were up to 12 or 13. We've gone back to 9 even as I say that now. I'll wait till we're at 12 or 13 before I think about sort of resuming. I'm just asking people if you've just joined us what scores we got. Well done, Matthew, an 8. Antonina, an 8. Paulina, a 10. Well done. And yes, if you remember which ones, you can say what they were now. In Max's case, it was the electromagnet one. You missed out the solenoid part. Right, so you mentioned the iron core. How, Harry, did you get 11 out of 10? That doesn't sound logical or possible. Go on, I want to know what you got the extra mark for. It was for solving the riddle of what stopped my internet. It could just be that he's magic. Of course, I haven't considered it. You are a wizard, Harry. Yeah. I think I've often mentioned the theory that even though I look like Voldemort, I'm obviously Professor Lupin, if I'm anyone from the Harry Potter series. we're up to 10. I don't know if that's a tentative 10. I don't know if that's a 10 that will now drop, but it might be a sensible place for me to carry on. And given that we have 20 minutes until the lesson would have ended, I think what will I do? Right, what I'm going to do is I'm going to save what we were doing. And even though it means me just standing around for a bit, what I'm going to do is I'm going to direct you to the questions. And then I'd like to go through the questions today, I think, because the last one especially is just a superb physics question. And it's one that I think you'll all struggle with, or some of you will struggle with, or you'll miss bits out if you're not careful. And so I really want you to have that experience of trying it. It's another of those, it's a 6-mark calculation, and you always know with those, 5 or 6 marks. And you always know with those that they are the most challenging sort of thing that you get at GCSE level physics. And so they're a really useful thing to try. So I think what we'll do, connection, if it stays up, we'll do this. What we'll do is draw our attention to those questions. Now, the ones I'm talking about start like that. They start quite simple. And I think the first page, well, the first bit of the first page might be quite simple. The bit that I think will be really interesting to you is question 2. There are only 2 questions altogether. Question 2 is quite a question. And so I'll be really interested to see how you handle that. So I am going to just shut up for a bit now. I'm going to give you, let's see. I think I'm going to give you 15 minutes. That may be excessive for someone. You're fine to chat to me if you're done through that and ask questions about physics or any of this equally. But I'll put 15 minutes on the clock. And we'll go through this after 15 minutes. We will do some more stuff on Fleming's left-hand rule next lesson. But for now, it will be just really useful to go through this. And I think it's the best use of the time we have. So thank you for bearing with me through all of that. 15 minutes of your work now. Off you go. There's a person either just arrived or just left. It's certainly gone from 9 to 10. So I'm really just saying this for that person's benefit if you've just joined us. The reason I'm not saying anything is I've given people time to work on the questions that I sent out. If you've got the right questions in front of you, then there's a picture of a left hand on the first one. I'm giving people, well, another 13 minutes. They'll have had 15 in total. So if you're the one who's just joined up, that's what we're doing. And if you've got these from your school email that I emailed out, then you'll be able to join in. There are only those two questions. It's possible. So normally people ask me that when they're near the end of what they've done. It's possible I've over-egged how long I thought these would take. I've gone on it by the number of marks. But yes, Harry, it's just those two. So if you got to the end of question 2C, and it is just 2C, it's not in any other part. So if you got to the end of question 2C, and you calculated the magnetic flux density, you've got to the end of the questions. What I'll do is I'll put on the screen some of my Fleming's left-hand rule problems. I'll hopefully do it in a less shaky way than before. And you can try and just practice Fleming's left-hand rule whilst others are doing that. I'll just put maybe 4 on the screen at a time and hope that they're big enough to see. Equally, oh, you've not finished yet anyway, Harry. What are the equations we need for 2C? Right, I'll come back, Harry. If someone's done, they can let me know. But the equations you need for 2C, well, I'll answer that to an extent without giving too much away. In 2C, you're given a wealth of information. But what I would say is the fact that you're given a clockwise moment tells you at least one of the equations you need. So if you know the moment equation, that's going to come in useful here. And then it gives you a few other things. It gives you a current. It gives you different lengths of wire to consider. You have to consider which length of wire you use where. But aside from that, so we've talked about the moment equation. Well, think about the equation we learned last lesson, I suppose, is my hint as well. And with those two equations, I think you can get a long way into this question. I hope I've not said too much to make this too easy. I don't think I have. Still a lot to do. But consider how those equations could work well together. We're up to 11 in the room. So if you'd been in the room before and then had seen that I'd had loads of connection problems, I apologise. If you're confused as to why I'm just standing around saying very little, that's because we're in the middle of practicing some questions. So if you have just joined, the questions we're practicing are these ones that I sent out. So if you have those, you can hop onto them now. You've still got 8.5 minutes. That might give you time to do most of them, I think. The one that's most difficult is question 2C. So perhaps start at question 2. If you've just joined us, start at question 2. You can always cycle back around to question 1. But question 2 is the really interesting one physics-wise. Harry, you don't need to know what the magnetic flux density is because that's what you're trying to calculate. So you don't need to know it to solve this question. But it in fact is the outcome. That's what we want to find out in the end. Up to 12, some of you will be getting bored of this pattern, but if you're the 12th person that's just joined us, then you've not missed too much with the connection problems we had. We're currently working through these questions. So if you're on my email list, you'll have those. And I would suggest if you've just joined the class again, start at question 2 and then go back to question 1, because question 2 is the one that is of real physics interest. Okay, right, now you're asking a good question now, Harry. So, what is magnetic flux? Well, I'm going to answer with a picture. Magnetic flux is basically, I'm going to start with my picture of a bar magnet. And to that picture, I'm going to add the field lines of force. And maybe to make my diagram complete, I'll just add arrows. They're not important for this, but it's a good habit to remain in. Right. But your question, Harry, was what is magnetic flux? Well, basically these lines are lines of flux. Flux is any area within the magnetic field where there is magnetism present, where there is a force due to a magnetic field. And that word flux density is just when you consider a certain area. So on this diagram, if I just choose first this square, there's a very high flux density. Lots of lines of flux are passing through that area. Whereas if I consider a similarly sized area up here, in that same size area, it's meant to be the same size roughly, in that same size area as the one down here, there is a lower magnetic flux density. So the flux itself, you can consider it to just be the lines themselves, the lines of force. But the flux density is how many of those lines pass through a certain area or through a certain volume if we're going three-dimensional, but through a certain area is known as the flux density. I hope that kind of answers the question, but it is a very good one. Now we're up to 14. So some of you are going to get bored of me repeating myself, but if you just joined back in because you were kicked out last time, I'm really sorry about the confusion. What people are still working on, with just under 5 minutes to go, is these questions. If you turn to question 2, if you've just got back into the room, skip to question 2 and start to have a look at that, because that's the real interesting one physics-wise. We'll go through the whole thing, and we'll go through the whole thing in 5 minutes, and that will be the end of this slightly disrupted lesson. I apologise if you had to be kicked out of the lesson because of my connection problems and have missed some of what's followed. But yeah, we're just in the middle of the questions. Field strength. How do you find flux density from field strength? These are equations from A level that do it. So it's another good question, Max. Yeah. Magnetic flux, and I'm glad of the question because I've not thought about this stuff in a long time. But magnetic flux uses the Greek letter phi. It's one of my favorites. And it's fairly simple, actually. To find magnetic flux from the field strength, from B, so I'm just trying to make sure this is in shot. There we go. From B, you times it by the area that those lines of flux are passing through. So yeah, to find what's called magnetic flux, and by the way, if you look at this, you don't need any of this for the question we're doing. This is just because Max and Harry are asking some good questions here. To find what's known as magnetic flux, it is just the magnetic field strength times by the area that those lines of field are passing through. When you get to A level, you'll start applying this to spinning motors. And because spinning motors operate at lots of different angles, then you start with that equation, but then you have to include a component, cosine component, to find the flux at any one point. And actually, to make this more general, because proper motors are made with lots of coils of wire, they have to drop an n for number of coils. And so you end up with that. N phi equals BAN. It's normally shown as BAN, not NBA, but BAN cos theta. And that is the molding at any angle, at any moment in a motor as it spins. I think I'm answering your questions as I hope you'd like. But yeah, that's the answer. You get from here to there by multiplying it by the area those lines of flux are passing through. Right, playing arrangements for tomorrow when we will do something new. So, once again, just going to switch the camera around. Hope this time the connection holds out. Okay. And as I go through these, I'm keeping a very close eye on the comments. So if anything isn't clear, or if you want to query anything, or indeed if you think I've got something wrong, there's every chance that I might make a slip up. If you think I've got something wrong, then let me know too. And I'm hoping this is more or less clear enough to see. I'm just going to check by adjusting the focus so that it's as clear as it can be. Right. Okay, so the first one, and you've got it in front of you too, which always makes it a bit easier. It says the left-hand rule can be used to identify the direction of the force acting on a current-carrying conductor in a magnetic field. And question A says, use the words from the box to label figure 1. And it's always easier perhaps when we have words from the box in which narrow down our choices, but I think you'd have found this fine anyway. This first finger represents the field. So you should have had field as your answer there. Even they've struggled with their own diagram, but this second finger represents the current. And this thumb represents, and from our choices, we don't have motion. I would accept motion if you put it just on autopilot, but from the choices, force is best. As I say, if you put motion there, I'd be happy with that too. Right, now you've not seen a picture like this before, or not one exactly like it, because we've not studied motors yet. We've studied the motor effect, not motors. We will go on to say a little bit more about them next lesson, but figure 2 shows an electric motor, and you can see there's this loop of wire that goes through a magnetic field. And it says draw an arrow on figure 2 to show the direction of the force acting on the wire AB. So particularly on this bit of wire. Well, what it's asking us to do is employ Fleming's left-hand rule. So we know from the diagram that the magnetic field is going that way. We know that the current is going that way. And that will allow us to work out the motion. We just got to get things lined up properly. So first, this finger here, the second finger, is the current. So that's correct. But once again, you can see we're in one of those slightly awkward positions. My first finger, the field, is going the wrong way. It's not pointing north to south. It's pointing south to north. So we rotate the whole arm. And we've still got current the right way now. We've still got the field the right way, and that leaves our thumb pointing downwards. What I think you should have labeled on this diagram, therefore, is something like that. And well done if you did. That wire AB will feel a force downwards. Next, part 2 said suggest 2 changes that would increase the force acting on wire AB. Well, we've not thought about it much this lesson, but don't forget F equals Bill. F equals Bill tells you the 3 things that could affect it. We'll talk about the first 2. So B, remember, is the magnetic field strength, and I is the current. They're 2 changes that would increase the force, F. If you increase B, you increase F. If you increase I, you increase F. We could talk about the length, but I'm going to talk about the first 2. So yes, we could increase, and it doesn't need to be particularly well worded, strength of magnet is fine. Just be aware if you put size of magnet. If you put size of magnet, that wouldn't be precise enough. Strength of magnet has to be the word there. The second thing is to increase the current. Those 2 things could increase the strength, increase the force acting on the wire AB. Part 3 of the question suggests 2 changes that would reverse the direction of the force acting on the wire AB. Well, again, be guided by the setup. We could either swap the battery around, or better way of putting that, perhaps reverse the current, or we could swap the poles of the magnet. And they're going to be my 2 answers here. So reverse the current, or swap the magnetic poles. On we go. And as I said, question 2 is definitely a difficult one, definitely the more complex one, definitely for that reason the more interesting one. So question 2 said, figure 1 shows a piece of apparatus called a current balance. And there's a lot to it, but we've got this horseshoe magnet creating a field here. We have this wire that's going into the field, and we have it balanced on 2 metal supports. And then there's an insulating bar at this end, which presumably provides some weight as well. And these 2 metal supports themselves form part of a circuit. And that circuit has various controls on it. It seems to have a thermistor, whether that comes up or not. It has a thermistor, it has a power source, it has an ammeter, it has a switch. There's a lot going on in that particular layout. When the switch is closed, the part of the wire labeled X experiences a force and moves downwards. So it's not clear for a start which bit it's referring to as X, but it means this whole bit. That whole bit is wire X, and that experiences a force and moves downwards. And anyway, part A asks, what is the name of the effect that causes the wire X to move downwards? Well done if you got that it is the motor effect. Question B then said that we were to suggest 1 change you would make to the apparatus in figure 1 that would increase the size of the force the wire X experiences. This in some ways is a repeat of what we had before. So if you wanted to increase that force, I'm going to go for 1 change. I'm going to put to increase the current. But of course, you might have gone for something different. You might have gone for increase the strength of the magnet, or increase the length of the wire in the field. Because remember, from F equals Bill, there are 3 things you can do to increase the strength of that force. Right, question C I think is the really interesting one, and the last thing we're going to go through today. And thank you for bearing with me, including through all the difficulties. But we'll make sure we go through this and we go through it well. So figure 2 shows a small weight now has been placed on this insulating bar. Figure 2 shows how a small weight placed on the insulating bar makes wire X go back and balance in its original position. So earlier in the question, this had all moved downwards. Now it's balanced because a small weight was put there. We're told a few other things. Wire X, and remember, wire X is this bit of it. Wire X is 5 centimeters long and carries a current of 1.5 amps. The small weight causes a clockwise moment of 4.8 times 10 to the minus 4 Newton meters. So this small weight causes a clockwise moment here. And then we're asked to calculate the magnetic flux density where the wire X is positioned and to give the unit. So when it asks us to calculate a magnetic flux density, what it's asking us is to calculate B. Let's think what other symbols we can attribute to things here as well. We're told a moment. Well, that would get a symbol capital M. We're told a current, and that would get a symbol I. And we're told a length of wire, and we're actually told 2 lengths. There's a length here and a length here. And working out what length to use and when is an important part of this question. This one here will help us with our moment calculation. This one here will help us with our magnetic field strength calculation. And this question brings those 2 calculations together. Let's think what we need to do to solve this. what we're trying to find in the end is the magnetic field strength, and that's going to come from the equation F equals Bill. Now, some of that we already know. Let's put in some of the things that we already know. We know, for example, we don't know B. That's what we're trying to find. But we do know from the previous question that the current was 1.5. And L, we know as well. The length of wire in the magnetic field was 5 centimeters. Well, of course, there's marks here just for making the correct conversion. 5 centimeters, don't forget, and I'm going to write it off to the side here, is 0.05 meters. So we know that that is 0.05. What we don't yet know is F. And that's where our second line of inquiry comes in. We're going to get F from the world of moments, because we have a moment and we have a distance. And so we can employ the equation moment equals force times perpendicular distance to pivot. And again, let's put the numbers where we know them and see if we can work out what we need. We know that the moment was 4.8 times 10 to the minus 4 Newton meters. So where M was 4.8 times 10 to the minus 4. Well, that equals F that we're trying to find, times by a distance. And the distance here, again, we have to convert it, but the distance is 8 centimeters. So 0.08. And just to show the conversion I did there, I'll just put the 8 centimeters equals 0.08 meters. So we're going to solve this one here, and then in so doing, we can bring our answer into this one and solve this one and get our answer. If we rearrange this, we have that F equals 4.8 times 10 to the minus 4 divided by 0.08. I'll just run that through the calculator. 4.8 times 10 to the minus 4 divided by 0.08. And you tell me if I'm wrong on any of this, but I make that to be 6 times 10 to the minus 3, or 0.006. You're fine to keep it in standard form. I'm just keeping in decimals. It looks easier when we plug it in. So now we know the force in newtons. We can input that answer into this equation, and in so doing we can then solve B. So where F was, now we can put 0.006, and that equals B, which we're trying to find out, times by 1.5, which we already knew, times by 0.05. I will always solve these this way, so I'm going to go through everything I would do. I would then make the numbers look as nice as possible by doing 1.5 times 0.05. So 1.5 times 0.05 just equals 0.075. So that means B, and I'm going to have to come down into this space because I'm working in felt tip. It just takes a little bit more room. B is equal to 0.006 divided by 0.075, and that equals again, if I've done that all right, and you can complain through the comments if not, 0.08. So my final answer that goes into that box there, I suppose, is 0.08. That's worth 5 marks, and the sixth mark is T for Tesla. And there you have the final answer. Now, no point me asking out loud, I don't think, and asking you to answer, but well done. Let's just say well done if you got that particular answer in its fullness. My guess is some people will have missed out the unit conversions and therefore lost 1 or 2 marks. but that most, I hope, will have been able to go through that and get at least some of it done, if not the whole thing. It was a tough question. So let me just turn the camera back and make some final remarks and some arrangements for tomorrow. Oh, and thank you, Max. You're asking something now. B is the magnetic field strength. Sorry, I can see the confusion here. There are two names for it, yes. B is magnetic field strength, but it's also sometimes called magnetic flux density. And I think only now do I see your queries from early on. Yeah, B is magnetic flux density, which we sometimes call at GCSE level magnetic field strength. They both essentially mean the same thing. That's the only other question I think I can see. So let me just make some final remarks. Firstly, sorry about the sort of connection problems that plagued the middle part of that. I'll go through some examples of Fleming's left-hand rule. I'm going to attempt to make a motor work on camera. I'll show you how a motor is built and attempt to make it work. That is very likely to go wrong. There's lots of things that can go wrong with that, but I'll give it a try. And we're going to talk more about how motors work and do some questions around that. But once again, for now, thank you so much for your participation on that and for the way you stuck with it. I'll be sending out a couple of things to print out by tomorrow, and I'll do that just after this. Just a couple of sheets to print out that will label up, a diagram to label, and then a worksheet to do. And so as long as you have that, we're starting at 9:10 tomorrow. So I'll be online from 9. The lesson starts at 9:10. It will finish at around 10:10. It should be another fairly tight one as well, assuming no connection problems. So for now, stay safe, look after yourselves. Thank you for participating once again, and bye for now. Bye.